Now, there have been theoretical calculations to form a star from an accretion disk, and this is shown here in this figure by Hughes, 1992, and there are some more recent calculations which essentially agree with Hughes, and they are displayed in this diagram. Here on the ordinate you see the mass. And as I told you, we are only interested in G stars, therefore we are only interested in this one line. And here is the distance in logarithmic scale in astronomical units. Now you see two interesting lines, the green line and the red line. And the green line, to the left of the green line, there is no planet, because there the temperature is so high in the accretion disk that the dust is evaporating, and so you don't form any planetesimals and planets. And then there comes the range of terrestrial planets, and here you have 5 of them. And then there is another line, this red line, and this is the so-called ice formation boundary or ice line. And here, the temperature in the accretion disk going away from the central object has fallen to very low temperatures, so about 150 Kelvin, and there ice falls out from the water vapor. And water vapor is a very frequent molecule in these accretion disks, and therefore a lot of ice crystals fall out. Actually, so many that the terrestrial planets forming here have masses of the order of 5 to 10 Earth masses. And this mass is then so big that it also attracts volatile gases like hydrogen and helium, and these are the most abundant gases in the universe, and therefore they very quickly, in a so-called runaway accretion, form gigantic planets, the Jupiter-type planets with 300 Earth masses. So beyond this ice formation radius, you form Jupiter planets. And out here you have these Kuiper belt objects, and they have little mass because here the end of the accretion disk comes, and there is not enough mass to collapse any great objects. But we are not interested in these objects. Okay, so this is the thing. So you have a few terrestrial planets, and you have these large Jupiter planets. Now we are able to make a sort of a short calculation, very rough calculation, how many Earth-like planets would you expect. Let's say our galaxy has about 1.6 times 10 to the 11 stars, and we said already we can only use G stars, and then we have a factor 0.6 because you need a high metal abundance element composition, meaning population 1, chemical position, because otherwise the terrestrial planets would be not big enough. Like the moon, for instance, at Earth's orbit, it's ideal in the habitable zone and everything, but the moon is devoid of life. So you need a big enough planet. So population 1, chemical abundance, and then you have to multiply with a factor of 0.3, because 70% of all stars are multiple systems. So you double or triple and what stars, and if you have a planet around this, the conditions are not stable over a very long time, and therefore we exclude these multiple systems. And here now comes the probability that a star, a terrestrial planet, falls into the continuously habitable zone, which has this small width of 0.06 astronomical units. This is the distance of the ice formation radius. So this is the probability of one star, but we have, as you recall, we have 5 planets. 5 terrestrial planets from these theoretical calculations. I put here only 2 because of these 5 in our solar system. The outermost one did not even form a planet because Jupiter, the tidal interaction of Jupiter, prevented the asteroids of forming a planet. And Mars has 1/10 the mass of the Earth. But you would expect for a terrestrial planet to close to the ice formation boundary to have more mass than the Earth. Yeah? So you see, Jupiter prevented Mars of having more mass. Yeah? And also Mercury is too close to the Sun, and the Sun perturbed Mercury so much that it also didn't grow massive enough. So we have this factor 2 here, and then we multiply with a very bad factor 6% here. Because of recent observations, and we were talking about this just now, you know, Jupiters are found, but they are not there where they have been formed at the ice formation boundary, but they have been found all the way in distances even below the radius, the distance of Mercury. How does a Jupiter go that far in? One now knows that has to do with Jupiter migration. They migrate in, but you cannot do that easily because you have to conserve the law of angular momentum. And the way a Jupiter does this is by throwing out a lot of mass and planetesimals which are orbiting inside, throw this out, and this way it can slowly go in, and the whole angular momentum is conserved. So if you then multiply all this together, you find very roughly 4 million Earth-like planets in our galaxy, which you think is quite a lot, but if you compare to the original number, you find that only 1 star in 50,000 stellar systems has an Earth-like planet. But if you multiply this number with the number of galaxies, in our universe, you find a number of 4 times 10 to the 17 Earth-like planets in our universe, and I wrote out this number here in detail that you will get impressed. You know, this many Earth-like planets are around, and this number alone tells you that we cannot be alone. It's no possibility that we can be alone. Let us now come to the next step and ask, well, given an Earth-like planet, how probable is it that life develops on it? We have to go back to the formation of an Earth-like planet. Here you see the Earth, which formed 567 billion years ago, and here this it has first a liquid surface, and then that surface dries up, becomes stone, and then the ocean deposits on top of it, and so on. And in the following graph, you see the stages for appearance of life on Earth. This is when the Earth and the solar system got formed. One knows this from a meteorite that fell in Kazakhstan. Then 40 million years later, the moon formation occurred as a collision of proto-Earth with Theia, which was a Mars-sized impactor. A Mars-sized impactor to form the moon, and then 4.45 billion years ago one knows that already oceans were on Earth, so it was cold enough in continents, and very likely there is a new paper in Nature in this year or the end of last year which claimed that the first living thing already happened at that time.